First objective, compare between functions written in implicit form and explicit form. Use implicit differentiation to find the derivative of a function. Most functions have been expressed in explicit form. For example, in the equation y equal to 3x squared minus 5, the variable y is explicitly written as a function of x. Some functions, however, are only implied by an equation. For example, the function y equal to 1 over x is defined implicitly by the equation xy equal to 1. To find dy dx for this equation, you can write y explicitly as a function of x and then differentiate. Look at the process. Xy equal to 1, and we move x to right side, so it's equal to y equal to 1 over x, and 1 over x can be written in power rule form, and we use power rule to differentiate, and we obtain dy dx. This strategy works whenever you can solve for the function explicitly. You cannot, however, use this procedure when you are unable to solve for y as a function of x. For example, how will you find dy dx for the equation below? For this equation, it is difficult to express y as a function of x explicitly. To do this, you can use implicit differentiation. To understand how to find dy dx implicitly, you must realize that the differentiation is taking place with respect to x. This means that when you differentiate terms involving x alone, you can differentiate as usual. However, when you differentiate terms involving y, you must apply the chain rule. Because you are assuming that y is defined implicitly as a differentiable function of x. Look at this example. Differentiate x cubed with respect to x. We can use power rule to get the answer. So the answer is 3x squared. But for b, differentiate y cubed with respect to x. The function variable is y. So for this case, we must use chain rule. Now I show you the process. For this case, differentiate y cubed with respect to x. Because of the variable disagree, so it can be written as differentiate y cubed with respect to y times dy dx. So this is the chain rule. So we can say d dx equal to d dy times dy dx. So we compare. Look at the left side. Differentiate y cubed with respect to x can be written as differentiate y cubed with respect to y times dy dx. Now look at C. Differentiate x plus 3y with respect to x. So the main function is in some or different form. So we straight away to differentiate. So we differentiate the x with respect to x. We have 1. Then to differentiate the 3y, we use constant multiple rule. 3 will remain, and we differentiate y with respect to y times dy dx. So we have 3 times 1 times dy dx. Look at this example. Differentiate x y squared with respect to x. The main function is in product form, so we use product rule. We differentiate second function with respect to x times first function plus we differentiate the first function with respect to x times second function. For the second part, for this second term, this is no problem to differentiate the x with respect to x. But for first term, differentiate the y squared with respect to x, which is the variable is not agree, so we use chain rule. We differentiate y squared with respect to y times dy dx. So we have 2y dy dx, and we simplify our answer. Look at the guideline. We have 4 steps. First step, differentiate both sides of the equation with respect to x. Collect all terms involving dy dx on the left side of the equation and move all other terms to the right side of the equation. Third step, factorize dy dx out of the left side of the equation. And lastly, solve for dy dx. Look at this example. Find dy dx for this function. Recall back the guideline given in the previous page. The first step is differentiate both sides of the equation with respect to x. So we write d dx and for the left side and also the right side. And then we realize that actually this expression is in some or different form. So meaning that we can straight away to differentiate for the each term with respect to x. And for the first three terms, the variables are not agreed. So we use chain rule for the first three terms. But for the last term, is agreed. The variable is agreed. So we can just use power rule. And the right side, just only the constant. So we use constant rule. Look at the chain rule here. For the first three terms, we differentiate the y cube with respect to x. So we apply the chain rule. We differentiate the y cube with respect to y times dy dx. And differentiate the y square with respect to y times dy dx. So when we differentiate the y square with respect to y, we just use power rule. And same for this one. This one is a constant multiple rule. So differentiate phi y with respect to y times dy dx. So we have negative phi dy dx because the negative is from here. And when we differentiate constant, we will have 0. For second step, collect the dy dx terms on the left side of the equation and move all other terms to the right side of the equation. Third step, factorize dy dx out. And the last step, we solve for dy dx. So meaning that we move dy square 3y square plus 2y minus y to right side. Or we say the whole equation divided by 3y square plus 2y minus y. Then we obtain dy dx. To see how you can use an implicit derivative, from the graph, you can see that y is not a function of x. Even so, the derivative found in example 2 give a formula for the slope of the tangent line at a point on this graph. The slope at several points on the graph are shown below the graph. Look at the graph here, and below the graph, the point 2, 0. Look at this point, 2, 0. The slope at this point is negative. And look at this point, 1, negative 3. Here, 1, negative 3. The tangent line, this is a tangent line here. The gradient is positive. The slope is positive, 1 over 8. To get the slope, we substitute the value into the first derivative function. Because the first derivative function is a slope function. And for the x equal to 0, look at this point. X equal to 0. It's a horizontal line. So that is why the slope is equal to 0. For the 1, 1, this is a point, 1, 1. The tangent for this point is vertical line. So that's why it's undefined. It is meaningless to solve for dy dx in an equation that has no solution points. For example, x squared plus y squared equal to negative 4. From the left side expression, this is impossible to produce negative value. And this is a circle equation. The radius impossible is negative value. If, however, a segment of the graph can be represented by a differentiable equation, then dy dx will have meaning as the slope at each point of the segment. Recall that a function is not differentiable at part A points with vertical tangent and B part points at which the function is not continuous. Determine the slope of the graph of this function at the point 3, 1. First step, differentiate the function both sides with respect to x. And on the left side, x squared plus y squared has a power square. So we use general power rule. Constant remain. 2 move to in front. And u n minus 1, 1. So the n is equal to 2. So 2 minus 1 is 1. And u prime. This is u. This is n. U prime. Meaning that we differentiate the u with respect to x. So our u is in some form. Meaning that we straight away to differentiate the first term and also the second term. When we differentiating the first term, we use power rule. But for second term, the variable is not agree, so we use chain rule. We differentiate the y squared with respect to y times dy dx equal to 100. Okay, differentiate the 100 xy with respect to x. So the 100 is constant, so we just remain the constant. And xy is in product form, so we use product rule. We differentiate the second function. Differentiate the y with respect to y. So we have 1 times dy dx times first function, product rule, plus differentiate the first function, differentiate the x with respect to x. We have 1 times second function, y. So from here, we simplify. After we simplify, we expand in and we collect. We move all the dy dx term to left side and the other terms to right side. Out dy dx and we solve for dy dx. We simplify our answer, and lastly, this is the answer. At the point 3, 1, the slope of the graph is as shown in figure below. Once we obtain dy dx, or we so-called the slope function, so we're able to calculate the slope. We substitute 3 into x variable and 1 into y variable, and we simplify. We have a slope is 13 over 9. It's positive value. And look at this point. The slope of this tangent line. And because of the tangent line is going out, so that is why its positive value. Find the derivative of this function. The main function is in fraction form, so we use quotient rule. But you can take in the natural logarithm for each side of the equation. Then we differentiate to get dy dx. Look at the procedure. Write the original equation and apply natural log at both sides. And because here the right side is division, it is the rational function, so we can use the natural logarithm property. After we apply natural log at both sides of the equation, and we can use the natural log property where we convert the division into minus. And from here, from this equation, we can differentiate both sides of this equation with respect to x. For left side, we differentiate natural log of y with respect to x. We need to use implicit derivative method because the variable is not agreed. And for the right side, since all the variable is x variable, so we just straight away to differentiate with respect to x. But you need to recall back the composite function. This is an inner function u, and as well as x squared plus 1 also is an inner function. After we differentiate, we simplify. After simplify, we move the y from left side to right side in order to get y prime. And what is the y from quotient? Then we simplify. This is the final answer.